Wonderful. Okay, good. And I changed my title just a little bit. It's the same content, but the topology I'll get to at the very end. So there will be topology at the very end, and I'll be focusing on the randomness and the frustration in quantum magnets. Actually, topology will be part of it.
So let's welcome Itamar. And first of all, thank you so much for agreeing to give an early morning talk. It must be around 7:30, I guess, there. So we look forward to hearing more about the recent developments and the interplay of disorder and frustration in quantum magnets. So let's welcome, and please, the floor is yours now.
Thank you so much, and thank you for having me. And I actually, thank you for organizing this this great workshop. And it looked really exciting. I was really hoping to be able to attend in person, actually, and but there were some things that came up. So this week, especially, was very hard for me, and traveling internationally is right now hard. So I still very much hope to be able to come in person another time. But I appreciate the opportunity to speak remotely. Actually, I realized, so I'm indeed, it's kind of earlier morning, so I'm speaking from my house right now. Actually, the print I have behind me, I realized, is a picture I took when I was in India a long time ago. So already, I feel in my office a little bit connected to ICTS Bangalore. So let me get to the physics. I'm hoping to tell you today about a kind of set of topics. It's a little bit broader, but I'll get to some specifics. And from those specifics, I'll try to kind of connect to other general topics that fit in this one theme, which is disorder, by which I mean the same thing as randomness, disorder or randomness, and the interplay of that with frustration in quantum magnets, in spin-1/2 magnets. And topology is going to come in as well. So just let's set the tone. I'll introduce my notation. I want to talk about frustrated quantum magnets. So I'm going to have singlet states, okay? And these singlet states I'm going to draw like this. So this is my notation. Can people see my mouse cursor? I wonder if I can make it into a better laser pointer. Is the laser pointer?
Yes, we can, yeah.
We see it. Great, wonderful. Good, so this is going to be my notation in different pictures for the singlet state. And actually, when I say singlet, I mean something more general. Sometimes I also want to have spin-orbit coupling. Okay, so this could be more generally a valence bond state, even when I have spin-orbit coupling, and even if it's not, if the usual SE2 symmetry that you may think you need for a singlet state is not there. Okay, and I can generally think of this. This is like the entangled state of two spins, right? In the ideal singlet case, up, down, minus, down, up. So of course, when I draw this, I might draw it one way, but I mean for the spins to be resonating. That cartoon with the blue ellipse means that the spins are resonating. Good, and then of course in quantum mechanics, whenever we have some kind of superposition, like in benzene, actually, whenever we have this kind of entanglement, we can have superpositions. So this is like a chemical bond. And if we have a bunch of chemical bonds, like in benzene, actually there can be different patterns. Often nature prefers those resonances. Very basic, but those are my ingredients. The singlet state and then resonances of the singlet state. And as the other basic reminder, if we think in 1D, I'm going to mostly talk about 2D systems actually today. But if we think in 1D, right, like what are the fates? Actually, early on the history, it was very confusing for people. When people asked if you have antiferromagnetic interactions between spin-1/2s, there's two possible fates. You could get this kind of classical magnetic order, which is a phase, and some corner of the phase is a classical product state of independent spins, or you could get this kind of pairing into singlets. Okay, and it's pairing into singlets. Of course, spin rotation symmetry is preserved. There's no particular axis in space that the spins choose. Previously, there was an axis they needed to choose. Here, there's no axis they need to choose. But actually, at least in this case, lattice symmetry breaking does occur. right? So we can see just from the cartoon that this spin needs to choose one of its neighbors to pair with. Entanglement is monogamous. It needs to choose one spin to pair with. Then we can fluctuate this. We can have quantum superpositions, but the basis needs to be a single spin. Okay, and so those ingredients. That's kind of what I mean by frustration. Frustration is a little loose, right? I can also talk about the degeneracy of classical Hamiltonian. I'll get back to that. But really, what I mean here with frustration is that the Hamiltonian prefers to have states that require singlets, require entanglement to be described. That's what I mean by frustration. And that's going to end up agreeing with other definitions like magnetic order temperature is reduced or eliminated. I'm going to care about the case when there's no magnetic order, and instead you get these states. And of course, as we know, then it's very hard to simulate these states directly. Very powerful people can indeed do simulations in 2D, but still there's some limitations. For example, gapless phases can be much more complicated to understand in 2D, and especially if I have a gapless phase that really has a long length scale, generically that phase can occur in some generic phase diagram, and efficiently simulating that phase on a classical computer in 2D or in 3D is basically impossible in the general case. So what I'm going to focus on is actually these kinds of phases where we need different kinds of tricks. The entanglement and that long range and gapless behavior requires us to have a different approach. We cannot directly simulate. We can complement what we do with simulations, but we need something else. And in particular, the way I'm going to get these states, and the other thing that makes things much more complicated for simulations and for analytical understanding, is randomness. So randomness, I can call it dirt, or I can call it the disorder. I'm going to think of this randomness occurring in the Hamiltonian as just a spatially modulated pattern. For example, if this is my spin half chain, maybe the interaction between spins, maybe it's still just nearest neighbor, but it changes. It changes strength. If there's spin-orbit coupling, it can change anisotropy from one bond to the next bond to the next bond. Yeah, it looks different. Okay, and of course, there's many ways we can get that. And kind of generically, we get it. You know, many materials need a little bit of substitution to stabilize, and then you get that. We care about doping. I'm going to focus here on magnetic insulators, spin 1/2 systems, but we know part of why we care about magnetic insulators is to ask what happens when you try to make them metallic. That's the recipe for high temperature superconductivity or other new kinds of phases that we don't even know how to think about yet. The kind of frustrated correlated metals, you can try to access them theoretically by doping a Mott insulator. But if I'm doping a Mott insulator, I inherently introduce disorder. Okay, so I'm forced to understand disorder if I'm going to look at any doped Mott insulators or many other materials. And there's a kind of neat thing that I want to point out, right? So here I'm going to look at a particular kind of disorder, which is kind of mild. I have a spin system, but am I looking at magnetic impurities? I'm not looking at magnetic impurities. So I'm not going to have any magnetic impurities in this talk. I have a very mild disorder, which is just this bond randomness. Or if you'd like, it's energy randomness. It's randomness in the coupling. Often it doesn't do much because it's a milder kind of disorder. Okay, but if I'm talking about frustrated quantum magnets that have these kinds of valence bonds, singlets, then the singlets, that's an object that lives on a bond between two spins, and my randomness lives on a bond between two spins. So I can think, okay, maybe there is some connection between them. Maybe I should make sure, I don't know if I can pause, like if people do want to ask questions during the talk, please interrupt me. Yeah, at any point. Okay, good. So to be concrete, let's say also have an experimental puzzle that we can try to understand. Okay, so this is some material you've probably seen also, right? The hydrogen modified lithium iridate. The lithium iridate is thought to be related to the Kitaev honeycomb system, like related to Kitaev honeycomb spin liquid. Maybe this material is as well, but let's just look at the experiments. They can measure heat capacity in temperature for different magnetic fields. These are the different magnetic fields. Okay, and you get different curves. But if you take all these curves, multiply each of them by b to the 0.5, then when you plot them as a function of t over b for each of these curves, all the curves collapse. And actually, we can see this is heat capacity. The phonon contribution doesn't collapse, but the magnetic contribution does collapse. And actually, if you kind of subtract the phonons, you can see it may collapse as well. Okay, so there's something weird going on here, right? Data collapse smells like a critical point, but this particular thing is not any otherwise known critical point. So that's pretty strange. Even stranger is that you can do the same thing for completely different magnets. Okay, so this was this Honeycomb-lattice spin 1/2 magnet. Here we have another spin 1/2 magnet, but it's very different. Here it's spin 1/2 on a triangular lattice. Microscopically, it's very different. Molybdenate, this is like a molecular magnet. Okay, but nevertheless, you do the same thing, slightly different exponent, and you get data collapse. And here phonons are subtracted. There's some nuclear spins that change the collapse and destroy it at low temperature. But you can, if you ignore the nuclear spins, then you can see the electron magnetic contribution seems to show this data collapse. Okay, so that's kind of shocking. Why would these such different systems have the same kind of scaling behavior? It's data collapse, and it almost looks like the same scaling function. And the only thing they might share is that both of them, if you study the material carefully, there's some randomness, and it's not magnetic randomness, it's non-magnetic randomness. Okay, so the spin system, all the spins are in place, no magnetic impurities, but there's some other atoms that are not magnetic that have some random positions, so they can change the energy or the interaction of the spins. So somehow that's the ingredient. Okay, but already there's a basic question. These systems, should I even call them both frustrated? So maybe you know the answer. Should I think of these two systems, are both of them frustrated, disordered quantum magnets? Is there that frustration as well? Of course, triangles are frustrating, but if I have a honeycomb lattice that's bipartite, then it wouldn't be frustrating, right? And I need that frustration to get my quantum entanglement. So probably you've seen the answer also many times in this workshop. But that was, I'll say, as part of that was my history in getting interested in frustrated quantum insulators, and in particular quantum magnets. That honeycomb lattice can have, when you have spin-orbit coupling, it can be very frustrated. Actually, it can give you, in a classical model, this has extensive degeneracy, and then when you make it quantum mechanical, Kitaev showed that actually there is a exactly solvable spin liquid that you can get. It is a Majorana-Fermion, and I'm talking about real materials. You might worry, like, how does this model connect to real materials? But now already there's been a decade of work, some of which I feel lucky I got to do earlier on after the proposal by Jackelli and Falulian, which was the big development, after they proposed that this can occur in some sodium and lithium iridate. By looking at the details of some of these materials, we could show that indeed this is an important term in the model. And there's different ways to argue for that generically, but for these materials, I think we have very good arguments because they're not spin liquids. They have some very strange spiral phase, very, very strange. Like if you look at the average S.S correlation, it's 0. Are the spins usually aligned or anti-aligned? On average, neither. It's exactly 0. so then you know Heisenberg term cannot be important, and actually then we can really rigorously show the Kitaev term it must be important there. Okay, there's many, so I'm talking about many projects, I should say, with many different collaborators. So I'm not even going to try to list all my collaborators, but I'll highlight some of the citations, and you can find other citations, like we have this annual review paper. Of course, there's many other reviews, as you've heard more recently, but this is some of the older work you'll find here since 2018. And also looking, so for example, looking at that Kitaev honeycomb model, there is the known Kitaev spin liquid phase, but we found early on in 2017 and 2018 that when you apply a magnetic field for the anti-ferromagnetic Kitaev model, that you get this other phase, which is gapless and exists between the spin liquid and the high temperature paramagnet. So there's very clearly, right, if you look at the numerics here, this is the MRG, very, very clearly, the imaging kind of like going towards 2 dimensions. Very clearly, the Kitaev phase is stable, and then there's the high temperature, the high magnetic field phase, the paramagnet. But then in between, there's very clearly some other phase. In this case, it looks unknown. We called it a possible intermediate phase in order to be rigorous, and we think it's a gapless spin liquid. And we did this work 5 years ago. Since then, there's been a lot of other work also seeing the same behavior. And I think now there's agreement that we could call it a gapless spin liquid, but gapless spin liquids in 2 dimensions, when there is that infinite length scale, it's very hard to be rigorous numerically. Okay, so now we run into this problem. We have some phase that looks like very quantum entangled, and we need to understand it. And even more so, this is relevant for materials, these Kitaev honeycomb magnets, like ruthenium chloride, where I think there's good evidence with sample dependence, etc., that disorder is important. So now we need to understand new kinds of spin liquid phases, like this intermediate phase, maybe gapless spin liquid in the Kitaev model with a magnetic field. We don't even understand this phase very well. There's really no way to understand it very well numerically without a quantum computer. You need some other tools. But the question posed by experiments is even harder. We need to understand it with disorder. Okay, so it's a phase with disorder. Yes.
So how do you induce disorder in any model Hamiltonian mathematically?
Good. So the disorder I'm talking about, the phase, the Hamiltonian we study here is just Kitaev with a magnetic field, and the Kitaev interaction occurs on all the bonds, and disorder is varying the strength of the Kitaev term on different bonds randomly at different points on the lattice.
Okay, thank you.
Yeah, exactly. And so there are also ways to study that disordered Kitaev model, but this phase we don't understand even for the clean case. People have studied it since our work. People have kept studying it for 5 years, and I think actually, I mean, there is a little more that is known, but it's very hard to have rigorous results for 2D gapless quantum spin liquids. QSL means quantum spin liquid. Okay, so that's maybe one motivation for understanding very generally frustrated quantum magnets with disorder. And actually, just very recently, just this summer, with collaborators, we have this paper on this material, which is a polymorph of tantalum disulfide. It's a 4HB structure of TAS2, which is like taking 2 standard TAS2 materials. One is an insulator, one is a metal, and you alternate them. Insulator layer, metal layer, insulator, metal. Okay, and this material they find is a superconductor at low temperature, but very strange things. There's some magnetic memory at a temperature above the superconductor. I won't have time to discuss it in full, but really crazy experimental results, which we think we can understand by saying that the insulating layers host a chiral spin liquid, then the metallic layers host a superconductor that interacts with a chiral spin liquid. But also in this material, there's also evidence for some disorder. So we don't discuss it in this paper quite yet, but we really, to have the correct theory, we need to understand the interplay of this chiral spin liquid with a superconductor with disorder, and maybe changes what we think is a chiral spin liquid maybe needs to change when you add disorder. Okay, and I think that's actually necessary to explain the it's truly crazy experimental results. Okay, so I said, if you want, you can look at the paper. We just put it in Nature this summer. So I'm kind of like putting there's many different things here. T-type honeycomb magnets, weird superconductors that have Mott insulator metal layers, and these different data collapse I was showing, right? So there's many different kinds of weird things to understand. So the hope is, can we have a general theory that can apply for any Hamiltonian, even if we don't understand the phase very well, like this intermediate gapless spin liquid phase for T-type model in the magnetic field? Even if we don't understand the phase very well, is there anything general we can say that's universal? Okay, by studying, for example, in this system, studying the interplay of valence bond with disorder. In this system, it might come from hydrogen. Other systems, it comes elsewhere. But very generally, what can we say about valence bonds in this way? Okay, so this is important context. So now let me define the problem that I'm going to say some specific things about. So I'm going to look at this Hamiltonian. Okay, can everyone see what my Hamiltonian is? You know what the important term is here? It's the second term is the important term. So it's dot, dot, dot. It's any Hamiltonian subject to some symmetry on some lattice. Okay, and I want this Hamiltonian to have a phase which is this frustrated quantum magnet phase that involves singlets. Okay, the singlets may be a liquid or a solid, but anyway, it involves singlets. So right now, let me turn off spin-orbit coupling just for this slide, and so I'll say there is a large energy cost to flip spins. Okay, so all the low energy physics for this Hamiltonian happens in the singlet manifold, just moving singlets around. It takes a large gap to break a singlet and open a spin. So everything happens in the singlet manifold, and now I'm going to just modify the Hamiltonian to add to slightly modify the strength of the coupling. Okay, weak randomness is what I'm going to look at, and I can even make it bounded, so I don't have any Lifshitz-Thales effects. Okay, weak bond randomness, and it turns out that there is some universal statements we can make that under certain conditions I'll describe, disorder necessarily leads to interesting low energy spin excitations. Okay, which I'm going to describe what I mean by interesting as I keep going now. And part of the answer here then is that it can be hard to simulate this numerically. So I should say there's also, since this work, this was also this, you can see some of what I'll talk about Anders Sandvik and other people have seen, for example, in quantum Monte Carlo, on certain Hamiltonians where you don't have frustration in quite the same way, so you can do quantum Monte Carlo, but you look at singlet states and you can have very large systems, and so you can see these low energy spin excitations that involve some long length scale. There is a long length scale here too. Okay, but here we're not doing numerics in quite the same way, so we really need a few different approaches. There's like spin liquid physics machinery, there's results from statistical physics and other results we needed to derive in statistical physics. And there's also things from quantum information that come into this. So let me say what I mean. Let's start with 1D as an example. I'm going to talk about, for simplicity, let me first focus on VBS phases. Okay, so for example, that's this phase. Whenever I have this phase, it's lattice symmetry breaking, so I have a partner domain. I have two domains, right? And there's spontaneous symmetry breaking between these domains. And I can have similar things in 2 dimensions. Simple like this or more complicated. So let me take one of these VBS phases in this domain, and now I'm going to add this order. Okay, and we know from what's called the Imrima that when I add this order, I get both of the domains. Okay, maybe that's the end of the story, But if we look very carefully, say I get the two domains, I get this domain here and this other domain over there, right? Then you can see the domain wall actually has a spin 1/2. And this is where topology comes in. It's in 2D, I'll argue more clearly, there is a deep, I'll call it topological reason for this domain wall to carry a spin 1/2. Okay, and once this domain wall carries spin 1/2, disorder actually creates a finite density of these defects that have some topology to them, and then these defects have to do something. In 1D, we know from work by Fisher that they give you the so-called 1D random singlet phase with a long-range entanglement. Okay, what happens in 2D? If you just look at the StatMake results, you might think that none of this story occurs. The domain wall doesn't need to have any spin defects, so that maybe, as you might expect, if the gap to creating spins is very large, and I add only weak disorder, I create the different domains, but I don't break any singlets. I don't have any spins. Okay, but actually what we find is that that's not the case. Under certain conditions, which is basically if the unit cell of the original lattice is odd, then we can show rigorously that there exist these point topological defects. You can call them vortices, and you can think of them as spin-ons if you want, but now they're frozen. They move around a little bit. They have some fluctuation, but they're not deconfined. Okay, they're the relics of spin-ons, these vortices, but like spin-ons, because they're really spin-ons, they have to carry a spin 1/2. Okay, and that spin 1/2 then is active. And this occurs no matter how large the gap is to spin 1/2. Even if creating spin 1/2 excitations was very expensive and we add very weak disorder, nevertheless, rigorously, this must occur. Okay, and it's because of these topological reasons, and I'll try to get to later on. Okay, let me skip some things, but so then what you end up getting is, as you do an RG flow, you add some disorder. You might think it has a weak effect, but actually, as you do the RG flow, the disorder has a huge effect, because now you have those spinful vortices, and you might get something like a 2D version of the random singlet phase. And then we don't know rigorously what happens to that exactly. Maybe there is a 2D random singlet phase. Maybe it becomes a strange kind of quantum spin glass. It would need to be a very strange spin glass. It may be a new kind. So the ultimate point, we don't know. Okay, I had a few slides. There's another limit where I can say rigorous statements that applies for like medium disorder on VBS or on spin liquids. What I just said earlier was weak disorder on VBS. We also have rigorous statements we can make for some medium disorder on spin liquids or on VBS. And that's true for any spin liquid. We can make these universal statements. And I don't have time to get into this in full, I think, but I'll say that we can study this problem. It's basically what we can do. We cannot look at any spin liquid with weak disorder, and usually they would be stable to weak disorder. But with medium disorder, I can think of the singlets like classical dimers and ask what happens to the classical dimers with disorder. And then I see the same kind of result that I get these spin defects appear. Was there a question? Okay, good. In this other regime of medium disorder on spin liquids, I end up getting the same answer. So either way, the picture I get as I do an RG flow looks like this. Yes.
Sorry, I have a question. So
yes.
In the previous slide, you said that the defect is topological, right? So why it is topological and what is protecting it? I mean, what is the invariant quantity for that?
Yeah, right. So what do I mean by a topology? So the previous vortex, I could call topological because actually, I'll say later, we have a kind of disordered, for this vortex, the condition for it to arise is that the unit cell before I added disorder has an odd number of sites. Okay, that sounds like a Lieb-Schultz-Mattis theorem. Lieb-Schultz-Mattis says if I have an odd number of sites in my unit cell, odd number of spin 1/2, then there's some conditions on the ground state. Here there is disorder. So Lieb-Schultz-Mattis theorem, which requires a unit cell, you need to throw it out the window. But we think that there is a different kind of Lieb-Schultz-Mattis theorem, a disordered version of Lieb-Schultz-Mattis theorem, that doesn't require translation symmetry in the unit cell. Instead, it only requires an average translation symmetry. So even when I have disorder, if it's like short-range correlated disorder, which is always disorder, that's what we mean by disorder, then there's translation symmetry on average. The ensemble of Hamiltonians has translation symmetry. Okay, and that's enough to define a different kind of disordered Lieb-Schultz-Mattis theorem that the result we have suggests should apply in 2D. And so we can prove this kind of disordered Lieb-Schultz-Mattis theorem in 1D systems. And in 2D, we cannot prove it, but this result suggests that it's there. Okay, that's what I mean by topology, because I can call Lieb-Schultz-Mattis theorem a kind of topological theorem. In this case, it's a little less clear for this regime. It's a kind of statmic problem. So yeah, depending on, there's some interesting thing going on that maybe I can also ascribe to topology, but it's a little different of a story. This is a new result we found that's purely classical statistical physics, that then we just apply to the quantum case. But it's a classical result. Okay, and I guess I'll say what the result is. You can ask, what's the critical strength of disorder versus spin gap at which you create spins? What's that transition point? And it turns out the transition point is at 0. So at any non-zero disorder, you create spins. That's the result in 2 dimensions. Okay, so now this is the picture we have. So now we can try to say, okay, what would be the prediction if you have, now we have these like spinful vortices or defects appearing. So generically, they should have some kind of power law distribution, but with a non-universal exponent. Okay, and this sounds like what we had before. There's some kind of, if we assume there's a distribution of these long-range singlets, like long-range singlets between these spins, not the short-range one, but the long-range ones. Assume some distribution, some power law distribution with some exponent gamma, then we get exactly what you had. So this is a theory we can have. It turns out spin-orbit coupling gives you a few different scaling possibilities for the scaling function. Okay, so there's a few different possible scaling functions. And in that sense, it's universal, but the scaling functions involve this exponent gamma, which is non-universal. Okay, so it's not quite like a critical point data collapse. There is a non-universal, there's a single non-universal exponent in this kind of critical point. But with that, if we extract that exponent from experiment, which is an independent experiment, then it matches and gives you the data collapse. Okay, so then we can understand this scaling function in data collapse for these materials. Okay, and we see it now, this is seen in a bunch of different materials. So these are the 2 I showed earlier. This is like the Kitaev honeycomb magnet. This is some triangular lattice spin 1/2 magnet. It's also seen in Hilbert-Smithite, we think. And also 1TTS2. This is some unpublished work, I should say. So don't copy this yet. But we see this, and actually for 1TTS2, usually we see the Q equals 1 scaling function. Here we see the Q equals 0 scaling function, which the difference is based on the symmetry of the lattice. Here there's enough symmetry to destroy Jelesinski-Moria interactions. And so what we get is the Q equals 0 scaling function. I plotted it differently here, but it's the same thing as what I call Q equals 0. Okay, so this is some particular scaling function. Okay, so now that we know that 1TTS2, which is some spin 1/2 multi-insulator on a triangular lattice, this is another spin 1/2 triangular lattice system, it shows this data collapse. Then going back to what we had before, this 4Hv is alternating layers of 1T and a metallic 1H structures of TST. And so in trying to understand this strange kind of magnetic memory superconductor, we need to understand this order, and we know that the 1T layers should be seen as some kind of disordered frustrated magnet, and so maybe there's hope to understand this whole structure based on building on the theory I just described. Okay, so this is work in progress. Good. And let me, I know I'm kind of running out of time. I'll flash very, very briefly. So the connection to topology, there is something even deeper that we can understand theoretically for all this. And that's what I mentioned with the Lieb-Schultz-Mattis theorem. And you can go to our, this is the PRX paper with Nahum and Senthil. I have, if you want to learn more, because I won't have time to fully describe it. But everything I just described can be thought of as a kind of disordered Lieb-Schultz-Mattis, which is a theorem in 1D, but right now is not yet a theorem in 2D. Actually, there's a very recent paper that was just posted by Chong Wang that has some other results. It's not quite, so it's another result that that goes towards having a disordered Lieb-Schultz-Mattis theorem related to what we do here. So I think it's a very exciting direction to understand the disordered Lieb-Schultz-Mattis theorems. And maybe I'll leave you with that. Why do I say Lieb-Schultz-Mattis has to do with topology? Because whenever I have a spin 1/2 system, I can think of it as coming as the topological edge state of a spin 1 topological phase, spin 1 Haldane chain, spin 1 SPT. Each spin 1/2 can be the edge mode of a spin 1 SPT. So all these statements, like this crazy thing we find in spin 1/2 2D systems, that even weak disorder immediately gives you this spin 1/2 excitations appearing in the long range entanglement between spin 1/2, even with weak disorder, right? These are, it almost says the spin 1/2 system really doesn't want to be trivial. It doesn't want to have like a gapped unique ground state. It wants to have gapless excitations. That's what Lieb-Schultz-Mattis theorem says, and that's also what surfaces of topological insulators have. When I have a surface of a topological insulator, the topology says my surface doesn't want to have just a gapped ground state. It wants to have gapless excitations. Okay, and the similarity of the TI boundary to spin 1/2, that's what I mean by topology in understanding all this. Okay, so we do a little, there's also some other work I'm working on that's related on TIs, but I'm going to skip it. And I'll just end with my conclusions because I'm really out of time. Okay, so there is some universal statements I was able to make here that can apply to a bunch of different Hamiltonians and a bunch of different materials. Okay, and that's what I can leave you with. So this is maybe a new kind of approach for how we can understand that interplay of disorder and frustration in quantum magnets in particular. Thanks.
Yeah, thank you, Itamar. Let's thank Itamar for a very nice talk. And yeah, we have time for some questions from the audience here. Okay. 1 second.
Hello. Thank you very much for the nice talk. I was wondering if you happen to know what kind of disorder is present in alpha ruthenium chloride. I know you were mentioning non-magnetic disorder things.
That's right. Yeah. So I mentioned alpha ruthenium chloride, and I should say, so all these materials that I mentioned that show this data collapse, alpha ruthenium chloride is not one of them. So I don't have any good evidence for disorder in alpha ruthenium chloride, but I know that there is a lot of sample dependence, and the low energy spin physics depends on the layer stacking and with sample dependence. So that suggests to me that some kind of disorder in, at least in the layer stacking, is having an effect on the spin physics. But that's a weaker statement for these materials. I mean, we have some prediction, very detailed prediction for the scaling function. We can see it, and none of that is seen in ruthenium chloride. And also, of course, ruthenium chloride at low temperature has magnetic order, so it doesn't have as much frustration as I need for this theory, because it does have magnetic order. Thank you for the question. Yeah.
Okay, so I have a question regarding renormalization time. So you remove certain degrees of freedom and then move from the Hamiltonian to the effective Hamiltonian, or you add a disorder in the coupling constant and the Hamiltonian themselves or the system themselves move from the one Hamiltonian to the effective Hamiltonian?
Good. So my at the beginning of the RG time, I have my spin Hamiltonian, and I add disorder to it. And then I ask, what's the low energy physics, the long length scale physics of that spin Hamiltonian that has a little bit of disorder? And I don't quite get an effective Hamiltonian out of it, because it's, well, I can describe it, but it's, this is like, if you'd like, you can do like a strong disorder RG. So it's still a spin system. The degree of freedom is still spin, but then like the physics you get involves these dilute spins that form long range singlets together.
Thank you.
Any questions from the physical participants here or the online participants? Yogesh, yes, please go ahead.
Hi, Itamar.
Hi, Yogesh.
Yeah. So, Mike, so your disorder is bond randomness then?
Exactly.
And in the hydrogen iridate and the other lithium molybdate, the actual disorder in the structure is in between the layers, right?
Yes.
So, for example, proton disorder in the hydrogen and so on. So,
yes.
Would, for example, if I take a Kitaev layer and let's say introduce disorder within the layer, like doping or something, wouldn't it also give bond randomness? So I am thinking if something can be said about copper iridate where the disorder is actually in the plane.
Right. So I'm trying to remember. I guess copper iridate also has some of the magnetic sites have substitution.
Yes.
So then it's like this disorder, but in addition to bond randomness, you also have like a site dilution, magnetic site dilution. So then actually, so I should say, let me say two things. So first, in some ways, you can say that's just a shortcut to what we get here. The theory I had was, even with just bond randomness, I end up with these like vortices that carry spin. But if you're just adding or removing magnetic sites, then already you can get these spins. So that's what I think happens in Herbert-Smithites in exactly that way. But actually, I should say something really important. When I have this theory and you get this data collapse, I'm not claiming that this is the only low energy physics. There can be other low energy physics that interplays and coexists with this. And this is the important open question that I really need to stress. But I do know that
could you elaborate on what else could be the low temperature physics? Some example?
Well, for example, maybe this can coexist with a spin liquid phase. Or for example, here I have actually a Mott insulator coexisting with a metal that becomes superconductor.
Sure.
This can coexist with a superconductivity in some unusual way.
I see.
Yeah. So even in the magnetic sector, maybe it can coexist with spin liquids.
Okay. Thank you.
Yes. Yeah. Thank you for the question. Yeah, I should look at the copper.
Yeah.
Hello. Yeah. So I was wondering that in these all examples you have shown, the spin liquid is basically a random singlet phase, which is a form of spin liquid. But I was wondering if one can think of free spin-ons in these systems as well, like which can coexist with the random singlet or be an independent, which is another different type of spin liquid. So
good. So, good, exactly. So you're asking, can I have free spin-ons here? And the word spin liquid is always a little bit ambiguous. Like some people might say this is yes, a spin liquid because it has long range entanglement and no spin symmetry breaking. Then it sounds like a spin liquid. Other people might say there's no fractionalization here, so it's not a spin liquid. And you're asking, can I have fractionalization coexisting with this? And that's exactly what I was saying. So here, the spin-on, there's no free spin-ons, no free spin-ons. But could I have free spin-ons coexisting with this? Maybe. And this is an important open question, exactly. So I don't know, but I hope we can figure it out as the community.
Okay, thanks.
Yeah, thank you.
See one raised hand, Sumiran. Yeah, please go ahead.
Hi, this is Sumiran from IIT Bombay. We applied this scaling collapse to a copper-based magnet, titanium disorder. It was quite disordered, 50-50%, in collaboration with Mahajan group here and Sharma group at IISc. The technical thing we had noticed that when we did the collapse for the ash measured specific heat and the magnetic specific heat, the gamma estimate was close but far enough apart within error bars. So I was wondering if you know, because in your Nature communication paper, it was as measured specifically in some of the plots. Yes. And do you have any comments on that?
Yeah, and say it again. I missed one word. So the magnetic specific heat and the what specific?
The as measured specific heat. You know, the total specific heat. So
with or without phonon subtraction.
Yes, yes. So
or
even
like
in your paper, some of the plots had the subtraction, some didn't have the subtraction, if I remember correctly. And
that's right, different materials, yes.
Yeah. In our case, we did it for the same material, and we noticed that the gamma estimate was 0.5 for as measured and 0.6 for subtracted, but they were not within error bar. So I was wondering if you have noticed something or had any comment.
That's interesting. And let me also try to understand, the subtraction is from fitting the T cubed or a reference material?
I think it was a fitting at T cube, but I am a theorist, so I'm not recalling fully.
Yes. Yeah, that's right. So that's very interesting. Maybe we should talk more offline about it. I mean, I know I have seen other cases where like there seems to be, they say like depending on how the fit is done, it's really tricky. And I've been like in one collaboration also kind of stuck on this point because I would expect that. Okay, let me also say one other thing. The exponent is allowed to flow. So calling it a single exponent is only like an approximate description. Really, as a function of RG time, that exponent could, in principle, flow. So it may not be a single exponent, which is then kind of not extremely satisfying. But so that may be the physical answer.
I see.
But in doing the fit is tricky. And we can talk more offline.
Sure. I'll write to you. But so, in other words, this e to the minus gamma exponent, the gamma itself changes with the energy scale. Roughly, that's what you have in mind.
Yeah, that's right. So this is really an assumption e to the minus gamma. So I should say, for example, if I just put spins randomly in space and I try to do like a strong disorder G, I have some. Then I assume some distribution. The distribution is log normal distribution, which isn't power law. At low the tail looks like a power law. But where exactly, what's the power exactly can change. And that's even just the starting point. Actually, when people do strong disorder G, it's kind of unknown what you get. And I was kind of brushing over that point, but in strong disorder G, you get some of these singlets, but you also get triplets. And when you get triplets, maybe this even leads to some spin freezing at some very, very, very ultra low temperature. Okay, so actually, all I know rigorously to say is the beginning of the RG flow. And then what happens afterwards, nobody knows rigorously. So there's open questions. We need experiments to answer the questions. The materials are the best quantum computers we have.
Okay, thank you. I'll write to you.
Oh, thank you. Yeah.
Bye.
Please go ahead. Yeah, Fabrice. No, you can go ahead first and then follow.
Hello. Yeah, I have just one quick question. Like from as you have shown this scaling behavior, and you have concluded that from the scaling behavior, the ground state will be a mixture of quantum spin liquid as well as the random spin singlet. So how do you conclude that from the scaling behavior of this heat capacity data?
Okay, so I do not mean to conclude that the ground state has a spin liquid and this random singlet regime. All I mean to say, what I can conclude is that the ground state, the low energy physics, includes random singlet type regime. And it's an emergent random singlet. Like sometimes random singlets that would mean like if I have magnetic impurities. Here there's no magnetic impurities, but I have emergent random singlets. And there may or may not be a coexisting quantum spin liquid. And from this, I cannot say anything about that. And it's even theoretically an open question whether that could be the case. But just directly, this, I think, gives good evidence, because this comes from the prediction of this emergent random singlet. So when you see it, it's good evidence that there is an emergent random singlet. Does that answer your question? So I cannot make a claim about a spin liquid or no, yes or no.
Okay, thanks.
Okay, yeah, I'm Fabrice Bers. Thank you for the nice talk. Maybe a comment and question. Since you mentioned Herbert Smith height, actually we did measure heat capacity in a higher field than before, up to 30 Tesla, and the scaling does not hold anymore.
30 Tesla.
The question is related: would you expect some limitation at some field for this scaling?
Well, absolutely, and it can come from different things. So, for example, here at large field, nuclear moments destroy the scaling. So that's one thing. But Herbert-Smith height is very complicated. So, for example, Herbert-Smith height is where, if I had to guess, I would expect that there is coexisting fractionalized spin liquids. By spin liquid, when I say spin liquid, I'm referring to like fractionalized spin liquid coexisting with this kind of emergent random singlet, because you kind of have these impurities. So I don't know how much the two subsystems talk to each other. So I don't know. It'll be really interesting to talk to you more, actually. So yeah, maybe it's just nuclear spins. Maybe it's other spin 1/2 behavior at low energies that maybe is a spin liquid, and maybe the interplay of the kind of emergent random singlet and what would be a spin liquid create a new kind of phase together that has its own behavior. Yeah, that sounds very interesting.
Yeah, okay, thank you. Well, it's not nuclear for sure, this we checked. And if I may, another small question. So you show picture of the emergence of this this pinon-like defect in the VBC picture. So this I understand if we have a valence bond crystal, but so you say that it should also exist for short range RVB ground state. And there, do you have a kind of picture or hand-waving argument where it should also be so in a liquid state, let's say?
Good. So in the liquid state, weak disorder in a liquid state does not give it. And usually liquid states should be stable to weak disorder. So it's only this intermediate disorder in a liquid state that can give it. So I hope that's clear about the claim.
Okay, I had missed it. Okay, sorry.
Okay, yeah, good. So let me be clear. It's only, I need strong enough disorder. So the hierarchy, I'll say, the hierarchy of scales I need here, the disorder, like earlier, the disorder is much, I can take it in this controlled limit. I can take it to be much smaller than a spin gap, but it needs to be much bigger than the energy scale of that resonances of the RVB. So actually, in the spin liquid low energy theory, it's strong disorder. But in the magnet, it's weak disorder. So I can call it medium disorder.
Okay, thank you.
Thank you for the, yeah, thank you.
Any more questions or comments from on-site or online participants? Okay, then we had a very interactive session here with the talk, and after that, it's nice. So it's a nice way to wind down the week. And let's thank Itamar again for a very nice talk. I thoroughly enjoyed it.
Thank you so much for the opportunity.
We look forward to having you in Bangalore next time.